Hi, fellow engineers. I'm Alex. I'm a software engineer from Republic of Moldova. Today, we'll try to work on a problem. Firstly, I found this problem in a YouTube video called Google Interview with a Normal Engineer. It was taken by Clement. Yeah, so let's dive right into the problem itself. Okay, so firstly, let's read it. Okay, so what do we have here? So we have a street containing blocks. In each block, there are one or multiple assets, including an apartment. So given a list of blocks and the list of requirements important for us, we need to find the block which will give us the minimum distance towards all required assets. Yeah, feels a little bit cryptic, though we'll try to digest it properly. So what do we have here? The inputs for our problem will be a list of requirements. So we have a gym, a school, and a mall. In the original video, it was used as store. I tend to rewrite it to be a mall to be clearer to draw the algorithm. You'll see it just in a moment. So we have the list of blocks in the form of JSON structure. So given the list of the requirements, so we'll have, if we have three requirements here, we are expecting to have three assets in the JSON format, like a flag, so like booleans. So in our case, in the first block, we have just a school. The gym and the mall are false. After that, we have the second block will have only a gym. The third one will have a gym and a school. The fourth one will have a school. And the fifth one will have a school. And a mall, yeah. So we'll have two assets. The output of this problem, it's expected to be 4. So let's try to solve it a little bit and understand why exactly it's 4. And let's try to come up with a solution for that. Okay, so I'll switch back to our drawing board and try to digest the problem. Okay. Yeah, so we are back on our drawing board. So yeah, let's start drawing. Yeah, what's more important in a software engineering algorithmic problem than to draw? So drawing is vital, or understanding what exactly we need to do. So first step in our solving will be just to understand what's the problem itself, try to manipulate a little bit the data, try to understand it. So we have 5 blocks. Yeah, let's try to draw 5 blocks in our case. So this will be block number 1, block number 2, block number 3, and block number 4. 4 and 5, yeah. So we have 5 blocks. So then I guess we'll need to add our assets. So we'll have 3 assets. So by S, I intended to be a school. So I'll just write S. For a gym, I'll use the G letter. And for a mall, we'll use M. Actually, this is why I've changed mall instead of store, because it would have been a little bit tricky to write it down. So we have S for school and S for store. So to not confuse people, I changed it to be a mall. So in the first block, we'll have a school. In the block number 2, we have a gym. In the block number 3, we have a gym. Actually, let's okay, so we can put a gym and a school. In the block number 4, we have a school. And in the block number 5, the single block with the mall. So we'll write it down because we have a school and a mall in this block. So we'll write things down. Now let's try to understand why exactly the solution for our problem will be this block, or the block with the index number 4. So yeah, So how to get into this problem? How to start to dig into it? So first of all, let's try to come up with a brute force algorithm, or let's try to solve it in our minds. So let's assume we are the solution for our block will be this the block at index 0, so this one. Let's try to compute the distances between our assets. So we have 3 assets. It's important for us to note here. So we'll have the school, we have the gym, and we have the mall. So we need to find out the distance. Yeah, the closest distance to these assets. So at index 0, so if you are here, the closest distance towards the school will be 0, because actually we are in the block. So in this block we have already a school. For a gym, the algorithm actually will be kind of the following. We'll need to start looking into the right for this block, and see if the next block has a 0, has a gym. Then we'll increment the distance by 1. So for example, we moved 1 distance here. So and we found out that the next block contains a gym. Then the closest distance between this block and the next one will be 1. For a mall, unfortunately, we can see that we need to move a little bit more. So we moved 1 distance. Then we need to move another distance, because here we don't have a mall. Then we move the 4th distance, and we moved kind of the 5th distance. And finally, we got here that we have a mall in the last block. So how many distances we moved? So 1, 2, 3, 4. So in this case, the closest distance from this block to a mall will be 4. Yeah, so kind of let's go to work on the solution for every one of them. Move it a little bit faster. So we have a school, we have a gym, we have a mall. So the closest distance towards the school will be 1, because either we move on the right side or on the left side. So we see that the closest distance will be 1. For a gym, we have a gym exactly in this spot. So the distance will be 0. And for a mall, on the left side, we don't have anything. So we need to move on the right side. So we see how many distances will be 1, 2, 3. So 3 distances will be, so this will be an 1, and this will be a 0 and a 3. So let's move to the index number 3. So we have the school, we have the gym, we have the mall. So we have a school here. Now we are at this level. So yeah, let me use another color. So we have the school in this block as well. We have a gym in this block, but for a mall, we still need to move on the right side. So we need to find it, and it will be 2 distances. So 1 and 2. Let's try to work on the block at the 4th index. So for the school, we have it here. For the gym, where do we have a gym? So if we're moving on the right, we don't have a gym at all. If we are moving on the left, we have a gym here, so it will be at 1 distance. And for a mall will be 1 distance, because we have the mall on the right side. So let's move on the last one. So for example, here we have the school. It's at 0. We have gym. We cannot move on the right side anymore because we don't have any blocks, but on the left side, how many distances we need to move? So it will be kind of 1 and 2. So the distance will be 2. And for a mall, we have a distance 0. So why exactly actually it's this block? Because we need to find out the minimum distance between our block and the given assets. So for example, the minimum distance for the mall in this case will be 4. Because kind of what we need to do is kind of find the maximum of all of these distances and assets and write it down as a solution. Because for this block, if we assure all distances, and in our problem, important for us is the mole as well, so we find out the max. So here the max will be 4, because if we want to get from this block to a mole, we need to work 4 distances. If we're moving into the next block, we see the distance to be 3. This will be the max. Then we have 2 here. We have 1 here, and we have 2 here. That would be the maximum. So the minimum distance needed to assure all of our requirements will be if we buy a house in this block. So we found our winner. So this will be our winner. Okay. I guess now what we can do is start working on an algorithm. So we'll not move to write any code for now, because still we need to dig into, let's say, our solutions and try to come up with an algorithm. So what exactly we need to do? If we go now with an optimized solution, it's not necessarily possible right first. So I guess we will need kind of to implement an algorithm which will follow exactly the steps which we did. So nothing fancy here. I guess what we will want to do is traverse the list of blocks or iterate them. So first thing which we'll write down. So if you're moving on writing the algo, let's switch the color. I guess use this one. So we'll write some pseudocode. So for each block, I guess we'll write down our blocks in the list of blocks. So assuming we have our blocks, we need to compute the solution. Yeah. So for each block, what we did in our problem, we computed a solution. So I guess what we'll do, it's write a function like, I don't know, we can abstract it. Maybe it's compute solution. Compute solution for this specific block. And I guess we'll need to pass out all the blocks, because the solution in itself, we need to traverse both left and right. So we'll pass the block and the list of blocks. I guess this solution will include it in a vector of solution, of possible solutions. So let's put s equal compute solution, then we'll include, so we'll have our list of solutions dot push our solution, so for each block. After that, what we'll need to do, actually, it's find the needed block, so the minimal distance. So we'll have another function, I assume, find mean distance. We can call it like that. And we'll provide our array of solutions. So this will be a high-level algorithm, because if you notice, so for example, the meat of our solution sits here in this compute solution part. So we'll try to expand on it. But when you are solving a problem, you first need to kind of try to divide it in smaller sub-problems. So for example, this will be one sub-problem. After that, we can work on compute solution to traverse on the left and on the right side the problem. So the meat will be definitely in this function, but for us, it's highly important as software engineers to try to, I guess, divide the big problem into the smaller chunks. Okay, so we come up with, let's say, the high-level algorithm. Now let's try to implement some stuff. So let's see the compute solution, how it will actually work. So let's change the color again. Let's use this. So we have the compute solution function. We have a given block. We have the list of blocks. I guess what will be important for us, I missed to put it here, it will be the requirements. Because without requirements, this will not make a lot of sense. So yeah, we have the compute solution. So now let's try to implement it. So what exactly do we need to do? I guess the solution for our block will be formed by what actually we did here. We traversed on the right side and possibly on the left side. If, for example, it's at index 0, if you are here, doesn't make sense to move on the left side. But if you're at the index, for example, 3 or 4, we definitely need to move on the left side. So we'll need to traverse our blocks. Yeah, we'll need to traverse our blocks on the left and on the right side. As well, we need to take into the consideration our requirements. Because, for example, in this case, everything was required. If you look here, so our requirements were everything. It's like a school, a gym, and a mall. It could be scenarios where it's provided for us only the school and the gym. It's not provided the mall, or a combination of these three, or even more requirements as well with more data. So let's try to write up the algorithm. Let's think on the algorithm. Let's look here what actually we did. So for each block, so assuming we are here at this block, we need to compute a solution in this form. So I guess for each requirement we'll need to write it down in some form of data structure. I'm not sure exactly what will be the data structure yet, though maybe some vector. I think it's a vector or an array. Makes sense, I guess, in this case. So let's see. So I guess we'll need to iterate again all the blocks. And kind of we'll need to do it both on the left side and on the right side. I'll try as well to write the pseudocode, but will be something on those lines. I guess let's try first to iterate on the right side, a simple thing. So for example, here we have for all the blocks, I guess, for the block, or let's say, to not confuse with this one, we need to provide a variable for that. Yeah, the hardest thing in software engineering is to find names. Let's call it B for now. For the B in blocks, or for the iterated yeah, let's call it just B for now. Let's not get very deep into it. Of blocks, or probably in this case we'll do it a little bit differently, because we kind of know the index of this one. So for let's say for an index, let's call it the index I of, let's assume we are at the index of this block index. Let's assume instead of block we'll have the index, or let's call it IDX, and then the distance will be blocks. On the right side will be len, if you write it in Rust. So this will be a range. So for this stuff, what we'll need to do, actually, it's take into consideration all the requirements. So we'll do another iteration, like for requirement of requirements. I guess we'll need to enumerate everything. So it will be like as well a requirement index. So Ri, I'll call it. So this will be a tuple of Ri, which will be the requirement index and the requirement itself. Then what we'll need to do is check if this requirement is enabled. I guess it's a true or a false. So in this case, we'll see if our requirement it's a 1. If yes, then we'll need to continue. Okay, I guess what we didn't speak about in the latest minutes, it's how exactly we'll structure our data, because this is vital. So what exactly it will be in our blocks? Because we're kind of defining the algorithm, but not clearly exactly how it will be defined. Because we have a JSON structure, but I don't think JSON structure will be good for us. First of all, writing it in Rust, it's a little bit cumbersome. So we'll simplify it, because I think we can write some clearer structure. So for example, for blocks, we'll use the following data structure. It will be an array of vectors, or an array of arrays in our case, and we'll do something on the following line. So let's assume we receive our requirements. So for school, if it's important for us, we'll write 1. And for the gym, if it's important, we'll write 1. And for the mall, if it's important, it will write 1, 1, 1. So actually, we not necessarily care much about what it's. Is it a gym or is it a what specific asset it is for us. It's important just to keep in mind the order. So we know that, for example, at the position 0 of the requirements it's the school part, at the position 1 it's a gym part, and at the position 3 it will be a mall. So let's write down a couple of them. So for example, for the first block, we'll have the school and pretty much it. So this means we'll write it 1, and for the gym and the mall, we'll write 0, 0. So this will be our first block. So let's write down the second block. The second block, we know it's just the gym part. So it will be a 0. So the gym will be the second position. So I guess you understood the idea behind it. So we'll get to the last one, which is the school and the mall. So school is the first, mall is the last, so it will be 1, 0, 1. So this means we have enabled, in our case, the school, yeah, we have the school part. So this will be the gym, which we don't have a gym, and the mall part. Okay, so we define the structure. So for the requirements, we receive it as a vector of length m. Let's put it this way. And the blocks will be n length. N will mean the number of blocks. And inside it will be another vector of size m always, where in our case, each position will be a different asset. Okay, so we came up to our, let's say, high-level algorithm. Then we iterate through our requirements. We have the requirement index, which we'll extensively use in our case, so keep in mind this one. We checked if our requirement is equal with 1. In our case, in our specific scenario, this one, everything is 1, so it's a bit redundant, but we may receive data where it's not necessarily 1 there. So it will be 0, so then we'll not need to compute a solution for that. So yeah, let's come up with the algorithm for the solution. So in our case, we'll need to define a variable for the solution. So let's call it let solution. Which will start to be first as a vector of data. So I get distances. So distances between, let's say, our block at index 0 and the given asset. So what finally we want to get is to build this structure. So instead of 0, 1, 4 in this format, I want to receive as an array of 0, 1, 4, where 0 will be the school, 1 will be the gym, and M or 4 will be the mall. So that's what I want to get back. So this will be our solution. So we'll start as an empty vector. I guess what we can do even further is to start everything to be at 0, because we assume that the distance is 0, so we can start it to be 0 first. So yeah, let's get right into computing stuff. So we are so our block. So this will be the block of the index. So we iterate through all the blocks. I guess now we need to check our block. So we need to check the block as well with the requirement index of this block. Because, for example, we are here at block 0. So let's look into this side. So this will be the block 0. And this on the top will be the requirement indexes. So requirement index at 0, requirement index at 1, requirement index at 2. So in our case, we can do the following stuff. So we have the solution at requirement. Actually, let's not do it like this. So first, let's try to find a 1 in our requirements. So we'll do an if the blocks of I, because I it's our index here, of requirement index equal 1. So if we found a 1 in our requirement, so we found 1 at the position 0, 0, it's a 1, then we found that to be a school. And for us, school is important. So this means we found a solution. So we have solution of Ri. Actually, it's not clear what to do here. We'll need to write some code. I'm not sure exactly what to write for now. But we kind of found a solution. So this means we'll not need to do anymore. We found it, so we don't need to increment it anymore. Else, though, if it's else, we'll need to increment the distance for our stuff. So blocks, actually not blocks, but it will be something like solution of Ry plus equal 1, because we are moving 1 distance on the right side, so we'll increase it to 1. And that should be it. But how can we mark it that we found a solution? Because this is a little bit troublesome. Maybe we should keep not only the distance part, but we should keep if we found a solution or not, to not iterate it anymore. So probably we need to do something like this. So so maybe instead of having this data structure, we can change it a little bit to make it a little bit more complex. So we can create an array of tuples. So for example, the first element of the tuple will be the distance part. The second, the Boolean, if we found a solution or not. So let's assume we start everything with false. The position 1 will be 0 and false. And the position will be 0 and false. So that will be the initial stage of our solution. So in this case, we'll have, so for example, solution Ri of 1, we'll just mark it as true because we found our solution. Okay, yeah. So if we found our solution, else we increment the distance. Though here, I guess there could arrive the problem because we may still find in the next iteration, because remember, we are iterating through all the blocks. We may still find our we may still find the same asset in some different block, and then we are increasing the distance, which is not correct. So probably this should be extended by, so if you check if blocks of index I of Ri equal 1, and we need to check as well if we didn't found a solution for that. If solution of Ri of 1, because the second element of our tuple, if it's false. So if we found this and we write it on the right side and we check if it's a false, then we found our stuff. Else, wait a second, that's not actually correct. So if this is for and this is false, yeah, then we mark as true. No, actually this part shouldn't be here. This part should be in the else part. So this should be an else if solution of Ri dot 1 it's false. Only then increase the distance, because this means we didn't found the solution. Else doesn't make any sense, otherwise we'll pollute our data. So yeah, we got our stuff here. So we got our solution, though this is only the solution for the right side. We need to do the same stuff for the left side to iterate our blocks on the left side, and this will give us let's say the left solution. So I guess we'll have two of them. So it will be our solution, and we'll have another one called left solution. Left solution, which will be kind of same stuff. So here I'm thinking maybe we can think of extracting function, because the iteration procedure, it's exactly the same, only the indexes changes. So I assume this part of the block can be extracted into a function. So I don't know, traverse, not sure how to call it, but yeah, let it be a function. Let's think of a name for this one. Compute local solution, maybe that will be a good name for it. Or yeah, find local solution. I cannot find a name in it. Find local solution. Yeah, it's not a right name for sure. Probably we'll need to find something, a better name for it, because this will be the same function pretty much. The single difference, it will be how we iterate through our blocks. So the range, it will be different. So that's pretty much it. So we compute our solution, the same algorithm as above. I'll not write it down. Just what we'll need to do is, instead of starting at index y, we'll need to move downwards. So we'll start at block of length this part, and I guess we'll need to write the reverse to write them on the reverse side, and then we'll move downwards to the index 0. So we have our two solutions. Now we'll need to write a function like find the minimum solution, like find the mean one. So we'll find mean solution again, mean local solution. We'll provide left and right solutions, and this will be kind of it. Pretty much that will be the whole algorithm on the high level side for compute solution. Okay, before closing with the whiteboard part, will be nice to look through the algorithm and try to come up with the complexity of the algorithm. So what did you found out here? So let's fastly see the time complexity first. So yeah, simple analysis. We have a for loop. We have the compute solution called n times in that for loop. Here we have find mean distance. So this will be kind of an iterations of each solution, because we'll need to check if this is the best one or that is, find the minimum part mainly. So here what do we have? We have another for loop, and we have another for loop inside for the requirements part. So if we call things the following way, so if we call n to be the number of blocks, dot len, and then m to be number of requirements, then our, let's say, big O, where the space or the time complexity of our algorithm will be something like n multiplied by n multiplied by m, because we have 3 for loops. So loop number 1, this will be n. Compute solution, we have another loop inside, which as well is iterating for left and right. Actually, this is funny because we are iterating through left and right, and we have something like n by 2 plus n by 2, and this will kind of be a full n. So we will just keep it to be n, because we are iterating on the right side once, and on the left side if we try to move, so it will be always 0. If we start at position 0, if we start in the middle, then it will be a full n. So always it will be a full n pretty much. So then the big O of our algorithm will be n squared multiplied by m, which is not necessarily a good algorithm. Maybe in the next part we'll be focusing first thing I'll be focusing on writing let's say writing down in Rust this algorithm, and after that we'll try to optimize it. Maybe we can squeeze some more performance, rethink the data structures. Maybe we don't need to do as many iteration or stuff, but for now this is what we worked on. This is the solution, kind of a brute force solution, let's put it this way. Okay, so we have n multiplied by n inside, n multiplied n, so this will be n multiplied by m, and we have n. So if we go on high level view, it will be n multiplied by n multiplied by m plus n, which is, this is kind of ignored on asymptotically, because we are trying to provide big values for n and m. And I guess if m it's a huge number, then we can write it down that this will be n cubed, which is not at all a good algorithm. So it'll be n cubed. Okay, so thank you guys. This is the first part, analysis of the algorithm, drawing down the algorithm on the whiteboard. On the part number 2, we'll be focusing mainly on writing it in Rust. So yeah, thank you.